The following differential equation is called a Sturm Liouville equation. Okay, and this includes many of the differential equations of mathematical physics as special cases. In other words, we can take many of the differential equations and try to put them in the form of the Sturm Liouville equation. Okay, and here we need to try to show that some of these differential equations can be written in terms of this Sturm Liouville equation. So we'll start with the Legendre equation, equation 7.2, which I copied here. So I'm going to show that this can be written as the above equation. Okay. Okay, so let's start with the Legendre equation, which is this. Okay, and let's see how we can put it in that form. Okay, we know that the original Legendre equation, right? First of all, I want to do one step here. Why don't I differentiate this? So if I differentiate this, I would get, using the product rule on the first term, I will get first as is ax y double prime, right? And then plus a prime x times y prime, and then the last term is the y double prime. So lambda b x plus cx times y, and this whole thing here equaling 0. Okay, so it probably just becomes easier for identifying the functions. Okay, so let's go ahead and differentiate equation 7.2 here. So we will get I will write the Legendre equation as 1 let me use the green, right? It's 1 minus x squared times y double prime minus, you could also differentiate this either way, you'll get the same thing, y prime plus l plus 1 y equals 0. Okay, so we can match now this green equation to the red equation. So we can see that ax is the coefficient of y double prime, which is 1 minus x squared. A prime x can come either from differentiating ax or by reading off the coefficient of y prime, which indeed is minus 2x. And we have the coefficients for y are L and L plus 1, right? So that means lambda bx plus cx would have to equal L times L plus 1, right? So that means the Sturm Liouville form of the Legendre equation will indeed be d over dx, right, of 1 minus x squared. So now I'm back to the original form of the Sturm Liouville equation that I have in the question. So this is d over dx ax times y prime, right? Close this. Plus, now the lambda bx plus cx, we said they're L times L plus 1, so L times L plus 1 y equals 0. Okay, let's move to the Bessel equation. So this is 19.2 that I wrote here. Let's change colors. Okay. Bessel equation. Okay, I'm gonna get rid of this first x here, so let me make this here a little bit bigger. whatever. So I'm gonna divide it by x, so I will get xy prime plus alpha squared. So if I divide by x, I get x here, right? And then p squared over x, okay, equals 0. Okay, so this is just a more useful form of the equation, and I could read from this, compare this to the Liouville equation, right? Liouville equation that's in the question. So we can clearly see that what multiplies y prime is ax. So in this case, ax is equal to x. Lambda, which is what multiplies b of x, right, is alpha squared. And so this is lambda is alpha squared with b of x being x, right, the first one, and then c of x, the second one is c of x, which is minus p squared over x. Okay, so now the Sturm Liouville form of this Bessel equation will be d over dx, right, of xy prime. So I'm filling into the Liouville equation here, the first equation, times or plus alpha squared x minus p squared over x, right? And this whole thing multiply, oh wait, I forgot the y here. So this whole thing multiplies the y equal 0. Okay, so we proved that this Bessel equation can be put in the form of Liouville. It is in the Sturm Liouville equation as long as we define a of x, lambda, b of x, c of x as such. Okay, let's go to the simple harmonic motion. And this equation is clearly y double prime equal minus n squared y. I could move this to the left, so I get y double prime plus n squared y. I could move the right term to the left, equals 0, and then I could read from this. I can compare and contrast this to my red equation, and I can read off my coefficients. So my ax would be 1, from which I can either differentiate to get ax prime, or I could read the coefficient of y prime. There's none, which makes a prime 0, right? And the coefficient for y is just n squared, so that means lambda bx plus cx equal n squared. Okay, and so the Sturm Liouville form of the simple harmonic equation, I could simply rewrite it as d over dx of y prime, because that is just y double prime, plus n squared y equals 0. Okay, now we'll go to the Hermite equation. So I will write it here. Okay, so far I have been reading a of x, differentiating to get a prime of x, and it's been matching beautifully such that I'm able to find those without any further work. In this case, it's not. This simple approach will not work. The reason being is because if I compare this to my red equation, I might naively think that the coefficient of y double prime is a of x. So in this case, the coefficient, so if I were to do this the wrong way, the coefficient of a double prime, y double prime is ax, so ax would be 1, which would make a prime of x to be 0, right? But the a prime of x is supposed to be the coefficient of y prime, which is minus 2x, so clearly this is not true, so I can't do that. So we have to think of something more of a sophisticated guess, and we would have to kind of bring in something such that when we differentiate it, it doesn't change. However, in the process of differentiating it, it would give us it would give us minus 2x. The first thing that comes to mind is e to the x. The first thing that comes to mind is e to the minus x squared. The reason being is because when I differentiate it, it stays there, and when I take the derivative of this, I get the minus 2x that's here in this equation, right? And then e to the minus x squared. So in other words, what I'm gonna do now is I am going to multiply this whole equation by e to the minus x squared. Okay, and if I do that, then my equation becomes y double prime times e to the minus x squared minus 2x e to the minus x squared y prime plus 2n e to the minus x squared y equals 0. And you can see now it works, because if my a of x, coefficient of y double prime e to the minus x squared, if I differentiate this, I get exactly the coefficient of y prime, which is minus 2x e to the minus x squared, exactly as it's supposed to be from looking at the Sturm Liouville equation. A prime should be the coefficient of y prime. Okay. And what else here? So now let's read off the so lambda bx plus cx would be the coefficient of y. So that means lambda bx plus cx would have to be 2n e to the minus x squared. And now I could put this Hermite equation back in its form, because now I can say that the first two terms, right, is d over dx of y prime times e to the minus x squared, because when I differentiate this by the product rule, I get exactly those couple of terms here. Okay, and so this plus 2n e to the minus x squared y equal 0. Okay, and now I could read, right? That's it. So basically, this is my my Liouville form, the Sturm Liouville form of the Hermite equation, right? And I could box this now. Of course, if we could read that lambda, which in the original Liouville multiplies the bx, right? So it could be the 2n that I have here. So lambda is equal to 2n, right? B of x is e to the minus x squared second. Yeah, and c of x is 0. Okay, let's move to the Laguerre equation. Laguerre, however you want to pronounce it. And this differential equation, the first Laguerre, so the first one, the first is xy double prime plus 1 minus x y prime plus ny equals 0. Again, here you can't say that ax is x, because that would mean a prime x is 1, which it's not, obviously, because the coefficient of y prime is 1 minus x. So we have to apply a similar reasoning to the previous question. And what I could do here, I could multiply this equation by e to the minus x. Okay, why is that? Because let me show you. Because if I do that, right, and the right hand side is 0, doesn't matter, and if I factor out e to the minus x, I could just divide by it and nothing in the differential equation changes. But how it helps is when I have x e to the minus x y double prime, so my a of x would be x e to the minus x. If I differentiate that using the product rule, I would get 1 e to the minus x minus x e to the minus x, which would be exactly the coefficient of y prime. Okay, so now I can claim that my a of x is x e to the minus x, and by differentiation that will get me exactly the coefficient of y prime. Okay, so now I could put it back into the Sturm Liouville equation, right? Which is d over dx. So I could rewrite this. Since I know that the product rule would generate the first two terms, I could rewrite this as y prime times x e minus x plus so this takes care of the first two terms, and then I have n e minus xy equals 0. This is the form of the Sturm Liouville form of the Laguerre first equation. And now we can compare this to the original and read off, provided that we read off that lambda is n, right? B of x is e to the minus x, c of x is 0, c of x is 0. Okay, now let's go to the second Laguerre equation. So the second Laguerre equation is, that's the second order, xy double prime plus k plus 1 minus x y prime plus ny equals 0. Okay, we're going to be used the similar reasoning as before, because if ax is x, a prime is 1, which is obviously not the case because we have k plus 1 minus x. So I would have to call a of x something. I would have to multiply this equation by something, and what that something is, I know it needs to regenerate the same derivative, so I know that my a of x would have to have in it, well, I need a minus sign to get the minus x, so I know it would have to have a minus x, right? And I need it to be multiplied by x. However, this time when I bring the exponent down, when I differentiate, it's supposed to give me k plus 1. So that means the x has to have a power of k plus 1 such that when I differentiate it, I will get k plus 1 x to the k e to the minus x, right? Because when I differentiate this a prime x, let me show you, I will get a k plus 1 x to the k e to the minus x, so product rule, plus or minus, because there's a minus sign, x to the k plus 1 e to the minus x. Okay, because this exponential ultimately disappear, and the x term for the y prime should only be x, right? So now if you were to, so that means I would need to multiply this original differential equation by x to the k such that I would get k plus 1 and e to the minus x. Okay, if I do that, I get the a prime to be exactly x to the k let's actually let me test it. Let's make sure. So now I have x k plus 1 y double prime, so I'm multiplying the x to the k e to the minus x n plus k plus 1 minus x times x to the k e to the minus x y prime plus n x to the k e to the minus x y equals 0. Okay, so oops, I forgot e to the minus x here. Okay, if we differentiate this, we get because this term here will just be k plus 1 times x to the k e to the minus x minus x to the k plus 1 e to the minus x. So yes, this would give me exactly, so this checks, this would give me exactly a prime. Okay, so it works. Okay, so this is just a verification that my choice of the multiplicative factor x to the k e to the minus x indeed leads to the same result. Okay, so now now I could just since I know that the first two terms will generate the derivative, the product rule will generate the first two terms, I could rewrite this now using the product rule backwards. So d over dx of x to the k, so now it's x to the k plus 1 e to the minus x y prime. I know that when I differentiate this using the product rule, I will get exactly these. right? This is what I just verified now a moment ago. So y prime plus I have n x to the k e to the minus x e to the minus x times y equals 0. So this is the Sturm Liouville form of the second Laguerre equation, and I could read off my lambda here. So my lambda obviously is n, right? My b of x is that function of x there, x to the k e to the minus x, and c of x is 0. Okay, so that's it. We have shown for the first part of the question, for part A, so this whole thing was part A, we have shown that all these equations, the Bessel's equation, the simple harmonic equation, Legendre equation, and Hermite equation, and both Laguerre equations, first and the second, could be written in the Sturm Liouville form. Okay, what's remaining to do now to part B is prove that they're orthogonal. Yeah, that if two solutions, if y1 and y2 are two solutions of the Sturm Liouville equation corresponding to values lambda 1 and lambda 2, then y1 and y2 on A and B with respect to a weight function b of x has to be orthogonal if this condition here is met. So let's do that. Okay, so let's do that. So I will so y1 and y2 are solutions of the Sturm Liouville equation. That means that differential equation will satisfy y1 will satisfy the differential equation, so will y2. So that means I could rewrite the Sturm Liouville equation for y1, replacing y with y1, okay, and for that I will use lambda 1 as to be the coefficient of b of x. We don't know what lambda 1 is, but it's some constant, plus cx. We're trying to prove this for whatever lambda 1 and lambda 2 this is. They would certainly be orthogonal. So this is for y1, and I'll rewrite the same thing for y2. I'll use lambda 2 as the coefficient of bx. Okay, now the trick is to prove something is orthogonal, I need to get to an integral. To get to an integral, I need to get an integral with y1 and y2 together. To do that, I need to basically put these two equations together, and the best way to get them together with the y1 and y2 included is to multiply the first equation by y2, because then I would have y1, y2, and I would multiply the second equation by y1. That way I also have y1, y2. Okay, and so when I do that, I will get the first equation to be d over dx and then the second equation becomes okay. So now I'm gonna subtract these two equations, and when I do that, if I subtract them, I'm gonna factor out the derivative, okay, and ax, both of them have ax times y2 y1 prime minus y prime 2 y1 okay, plus, so this is all inside the derivative, plus so now when I subtract here, oh oops, wait, this is 2, so I'm gonna get so factor out b of x y1 y2 lambda 1 minus lambda 2. Note that c of x y1 y2 minus c of x y1 y2 goes away, so I'm ending up with this. Okay, so now what I'm gonna do is I'm gonna integrate from a to b, since I'm trying to prove that this is orthogonal from a to b. So I'm gonna place an integral here, so from a to b d over dx okay, ax y2 y prime 1 minus y prime 2 y1 plus, okay, since this is a plus, I'm gonna do this in one step, so I'm gonna split this up into two integrals. So this whole thing of course is integrated with respect to x, so this is dx, okay, plus that plus sign is here, the integral, and from a to b b of x y1 y2 lambda 1 minus lambda 2 dx, and this is equals 0 of course. Okay, now notice that this dx and this dx goes away. So by fundamental theorem of calculus, number one, when I integrate an equation as a function of x, if I integrate the derivative, this is the antiderivative and this is the derivative, I basically get the integrand, what's inside. So I get whatever is in here. So if I apply this to the left part, the first integral in my equation above, I will get just ax right, y2 y prime 1 minus y prime 2 y1, so that's the integrand evaluated from a to b. Okay, so integrate the derivative, you get the function itself before it's being differentiated, plus the integral from a to b of b of x. Now lambda 1 minus lambda 2 is a constant, so I can pull it out. So b of x y1 y2 dx equals 0. Okay, now the question stipulates, if you look back, that this would be orthogonal as long as a of x y prime 1 y2 minus y prime 2 y1 evaluated from a to b equals 0, meaning the first component here the first component, if this guy goes to 0, right? So if this equals 0, then I would have left lambda 1 minus lambda 2 integral of a to b bx y1 times y2 dx equals 0. So either lambda 1 equal lambda 2, which would then means that y1 equals y2, and this is a trivial case because we're talking about the same solution. Otherwise, so if this does not equal 0, therefore a to b, the second one has to be 0, b of x y1 y2 dx equals 0. And since the integral of y1 times y2 weighted over the function b of x equals 0, therefore we've proved that hence y1 and y2 are orthogonal. With respect to weight function b of x, because that's the function that's left inside the integral. This concludes the proof.